Good morning, everyone. This video we are covering 7C, 7D, and 7E. 7C, the law of large numbers. 7D, assessing risk. 7E, counting and probability. Some of the contents we are going to talk about, we have seen them from previous videos. But in this section, we are going to look at them a little bit closer. The first topic, the law of large numbers. In order for you to best understand the law of large numbers, let's look at an example. Law of large numbers. Let's look at an example. Let's say this is how do we define a trial. Here, we consider the trial is to flip a coin once. And now I'm gonna repeat the trial many times. Repeat the trial n times. And we consider the proportion or the percentage of getting ahead. Consider the percentage of getting ahead. Then let's think about if we let X be the number of successes. Then the sample proportion. Do you guys still remember the formula? Sample proportion equals X over N. We are actually collecting a sample. You flip the coin once, you would have a result, right? And you flip it another time, you would have another result. You flip a coin n times from the n trials, then you would have a sample with the size n. The data in the sample either head or tail. So if we let X be the number of successes here means head, getting ahead. Then the percentage of getting ahead, or the sample proportion, would be X over N, number of successes over the sample size. Do you agree that? Okay. Would it be approach to the actual value of getting ahead? We know if we flip a coin, the probability of getting ahead is half. We all know that, right? 50%, 0.5. And it turns out, if we repeat the trial big enough, then the percentage of getting ahead, or the proportion of getting ahead, would be very closer to the actual probability of getting ahead. As n approaches infinity, actually P over X over N, which is also the relative frequency, approaches the actual probability. As it says here, if the process is repeated through many trials, the proportion of the trials in which event A, in our example A would be getting ahead, occurs will be close to the probability of A. The larger the number of trials, means n, the larger the number of n, the closer the proportion should be to P of A. That is how do we understand the law of large numbers. I want you please relate this example with the law of large numbers. This is a pretty simple, straightforward, and a very useful example. The second definition of probability, the empirical probability, another name is the relative frequency approximation, is based on the theory of the law of large numbers. Alright, let's move to the next topic. Expect the value of a random variable. We have introduced, we have learned what is a random variable, right? We bring in random variable to represent the population in statistics. In order to find the expected value of a random variable is brought in to numeralize the experiment's results. Okay? And I showed you in previous videos the formula to find the expected value of the random variable x. It actually represents the center of all the values could be represented by x. The expected value can be found by following this formula. We need to construct the probability distribution for the random variable first. The random variable here actually is discrete. Make it even more accurate for you. Discrete, C-R-E-T-E. We are talking about, when we talk about probability distribution, the probability distribution is the distribution of a discrete random variable. We have two types of random variables, discrete and continuous. And so far, especially when we talk about probability distribution, we refer to discrete random variable. What does that mean? That means all the values that x could assume are either finite or infinite but countable. That means you could list the values for x in column 1. If it has continuous values like uncountably, there's not possible for us to list those numbers in the first column, right? Does that make sense? So we are talking about discrete random variable. In the first column, you list all the possible values for x. In the second column, you find the corresponding probability for the random variable assume each value. Once you have the probability distribution, then you are ready to compute the expected value of the variable by following this formula. How do we do that? You multiply x1 by its corresponding probability, p of x equals x1, plus x2 times p of x equals x2, plus and so on, plus x sub n multiplied by the probability of x equals x sub n. Okay, I think the best way to understand the process for the formula is to apply it. Let's see two examples. Please pay attention because those two examples are your day quiz problems. Number one, 15 people gather for a hot dog eating contest. In the past, 8 of these contestants have eaten 37 hot dogs during the competition. 3 ate 43, 3 ate 47, and 1 ate 49. Those are historical data. What's the expected number of hot dogs eaten by a randomly chosen contestant today? Let's figure out the goal. The goal is the expected number. It's actually the same with expected value of hot dogs. Expected value of the number of the hot dogs. Okay, so we are looking for the expected value of a random variable. What is the random variable here? What's the expected value of number of hot dogs? So x here, let me write it down. X here is the number of hot dogs. Yeah, it's right here actually. I have it. X here represents the number of hot dogs eaten by a randomly chosen contestant today. So that's the goal. We are clear about that. In order to find the value for expected value, in order to find the value for E of X, we need to construct the probability distribution first. Probability distribution table first. Distribution table first. The table has two columns, right? So we have two columns. The first column, we need to list all the possible values for X. All that we have are historical values from past. 15 people gather for a hot dog eating contest. In the past, yeah. So in the history, 8 of these contestants have eaten 37. So that means 37 was a value of X in the past. Do you see what I'm saying? So 37 is a value that X could assume. If we read on, 3, 8, 43. So 43 is another value that X could assume in the past. 3, 8, 47. 47 is another value that X could assume. And 1, 8, 49. 49 also is a value that X could assume. No more. Okay, so far so good? The first column of a distribution table, we list all the possible values for X. In the past, we know X could assume those 4 values. That's the first column. Second column, we need to find the probability for variable X assume each single value. Let's see the first probability. What's the probability that X assumes 37? I would maybe explain here. I think you could see that, right? Yeah, you see all the things here. We need to figure out P of X equals 37. It's a probability. Whenever we need to find a probability, we need to consider what's the model? Theoretical model, empirical model, or just the subjective? We have the historical data, so that is empirical. All right, so that is empirical. So we are going to use the frequency, relative frequency, or the sample proportion to estimate the probability. We have just talked about the law of large numbers, the definition of empirical probability. So in the past, so for all the computations, 15 people gather for a hot dog eating contest. So I would believe always have 15. Let me read it again. 15 people gather for a hot dog eating contest. In the past, yeah, okay. So basically you have 15, you have a sample with the size 15. In the past, among the 15 people, how many of them ate 37 hot dogs? 8 of them. Number of successes, 8. 8 people ate 37 hot dogs among the 15 people. So that is the empirical probability. Do you see what I'm saying here? The probability that X equals 37 is 8 over 15. This is a proportion or percentage. It is the empirical probability based on the historical data. And the probability that X equals 43. In the past, among the 15 people, how many ate 43? 3. So 3 over 15. That's the probability that X equals 43. P of X equals 47. In the past, among the 15 contestants, how many ate 47? 3. Again. So 3 over 15. P of X equals 49. In the past, among the 15 people, how many ate 49 hot dogs? 1. So that is a 1 over 15. All right, so we put those numbers right here. Match the values for x. Be very careful the order. There's not correct to mess up. That is very important not to messing up the order of the values. So once we have the probability distribution, we are ready to find the expected value by the formula. So this is how do we do that. We multiply 37 by its probability. The yellow times green plus yellow times green plus yellow times green plus yellow times green. So 37 times 8 over 15 plus 43 times 3 over 15 plus 47 times 3 over 15 plus 49 times 1 over 15. You might notice that I didn't reduce 3 over 15 here, even we could. It equals 1 over 5, right? But the reason I didn't do that, the reason is because I want to keep the denominator the same. Now they all have the same denominator. All I need to do is to multiply the top, 37 times 8, 43 times 3, 47 times 3, 49 times 1. Keep the denominator and add the top up. We end up with 41. How do we understand? So the math part, I would leave you to figure out the fractions, operations of fractions. How do you apply your calculator to get the same result? Let's explain or interpret 41. How do we understand that? We found that the expected number of hot dogs eaten by a randomly chosen contestant today would be 41. That means, based on the historical data, in a contest, if you randomly select a player, you expected him to eat 41 hot dogs. Okay, 41 actually is the center of the values of the numbers of the hot dogs eaten by the contestants in the computation. Is that understandable? If you concern what's a professor's class you want to take, you concern on average the letter grade that the students get from the teacher's class, right? So because, for example, if averagely speaking, students get a B from the class, then you would expect yourself maybe get a B as well. Does that make sense? That's how do we understand expected value. The second example, a casino card game takes $3 bet. Players have a 45% chance of winning. Winning back their bets plus $3. And they have a 55% chance of losing their bets. What's the house edge? Well, we have to explain what is house and what is house edge. House here means a casino. So we are going to think for the casino. We're going to calculate the expected profit for the house. Okay? So here we are going to consider the profit that the casino would earn if the player bet $3, because the bet for the game is $3 here. Okay, so we're going to think for the casino from the casino's perspective. We are looking for house edge. The house edge actually is the expected. House edge actually here is the expected profit of the casino for your $3 bet. So we are looking for E of X. Then we need to figure out what is X. X here, as I wrote here, X is the profit. X here is the profit. X here is the profit of the house, or the earning. Earning is earning the same with the profit. I think similarly, right? Okay, so in order to find the value for E of X, we need to construct the probability distribution first. it is a 2-column table. Column 1, we list all the possible values for x, the possible values for the profit. So what is it? If the player wins, then the casino loses. Loses how much money? Loses $3, right? So the player bets $3, and if they win back their bets also another $3. So the casino would lose $3 if the player wins. And that chance, that probability is 45%, which is 0.45. And what if the player loses? Then the casino wins. Win how much money? How many dollars? $3. Okay? They bet $3. If the player loses, then they lose the $3. Then $3 would be the casino's income. And that chance, that probability would be 55%, which is 0.55. So now we have the probability distribution. We are ready to compute the expected value. We multiply -3, be very careful with the sign. We multiply -3 and 0.45 together. And we multiply 3, 0.55 together. And then we add them up. We end up with 0.3. $0.3. So that is 30 cents. 30 cents for $3 bet. Then for 30 cents for $3 bet. And what if then if we divided everything by 3, then that would be 10 cents for $1 bet, for $1 bet, right? So we should choose 10 cents per dollar. That's the house edge. That's what does the casino expect to gain from the players. Many players, right? Many players play many games. For each dollar that the player bets, the casino the casino expects to earn 10 cents. 10 cents is 0.1. So let's see, 0.1 over $1. That is 10%, right? Well, that's pretty good. Yeah. All right, so that is expected value. We're going to stop here and start a second part.